So you are good to go. Okay, proceed.
Okay.
Okay.
Yeah, we start.
Mm, mm,
Yeah, so somehow the previous lectures content were not saved. I'm not sure what happened there. So in previous lecture, what we saw that in previous lecture, what we saw is not saved in this one file. I was saving everything in this one file, but it is not uh, saved. I will just quickly, I just opened this file and I got to know that they are not saved. I'll quickly, and anyway, it is 2 weeks. After 2 weeks, we are doing it again. So I will quickly revise what was done, and then on that, I have to add about matched and unmatched disturbances with an example. So today we are supposed to look at matched and unmatched disturbances and how they figure into this sliding mode, sliding mode model, etc. Um, so, so what we saw was we had taken this system which is in control affine nonlinear form with x in Rn and u in R, single input system, and then we had this switching function which is function of x, and we had also taken this to be a single function from Rn to R. Okay, and then we had computed sigma derivative with time, that comes out to be something, some function of x. mm, or in last lecture we had started looking at disturbance, so we had a disturbance also here. Let me write disturbance also. Like, and then with this disturbance, uh, we have some disturbance terms in this fx and gx both, and we will assume this disturbance to be bounded by a real number. Okay? This is some real number known, and dm is supposed to be known. Okay, and then we can find the sigma derivative which will be in these terms, fx plus gxu. We will get this fx will have some terms of a, gx will have some terms of bx combined with b and all. So whatever the structure, we'll see one example. Now after we arrive at this form, um, we assume, we put some assumption, boundedness assumptions on f and g. We assume that fx is bounded on both the sides by a number f which is known. We know this f, and gx is bounded below by some number g small m, okay, which is also sign definite. So we will put like this. Okay, and if we put this assumption, and we assume this boundedness, and we assume this f and g small m both we assume to be known, then we can stabilize this equation. Let's say this equation is 1. We can uh, we can say u is equal to minus k sine of sigma stabilizes 1 in finite time if k is greater than uh, f by g small m, right? And we had seen this how this happens. We had actually derived this condition. Uh, so we had derived that if we put k is equal to, if we select k such that it is greater than f divided by gm, then simple this control, and this control is so simple in nature. There is no complicated equations required. There is no calculations required. It is just a switch. Signum sigma is a switch. It is a relay multiplied by a gain. So just a gain and relay can stabilize this sigma in finite time. And now we look at the system. System is general non-linear system. X dot is equal to ax plus bx u plus disturbances. We may not know what is ax, we may not know what is bx, we may not know what is dx. Knowledge, exact knowledge of any of these functions is not required here. We just need to know the general bound in which these functions values may remain. And if we can get those bounds by looking at the bounds on states, right? So then we can design this very simple control, and that can make sigma 0. And when sigma becomes 0, what happens? When sigma t becomes 0 and stays 0, zero dynamics becomes active, and those are designed. And I'll just write ZD. ZD are either designed to be desired or assumed to be stable, right? So once you make sigma 0 using this control is guaranteed to make sigma 0 if k is having these conditions. If k is uh, uh, designed according to this condition, then this control will definitely make sigma 0. And when sigma becomes 0, you have zero dynamics, and which is stable, or they are something that we had designed already earlier. Okay. So now then the question comes that those who have looked at sliding mode control earlier, uh, then in the sliding mode community always people talk about matched disturbance and unmatched disturbance, and sliding mode can reject matched disturbances, and unmatched disturbances cannot be rejected, or you can do something boundedness with unmatched disturbances. So where does that come? Here we have not put any matched or unmatched or matched condition on dx here. So this disturbance has no condition apart from being bounded and the bound to be known. There is nothing else we have put. It is very general problem, and we have proved this theoretically that this happens, and even with any kind of disturbance we can achieve finite time convergence on sigma. So with that,
Prasid, uh,
yes.
so when you say one is stabilized in finite time, so see, we have not shown any proof or convergence of finite time stabilization,
Yes,
right?
yes, yes, exactly. Yeah, I know. And today I was in dilemma that what to take.
Uh,
So earlier we have talked about the finite time convergence of this equation.
uh,
So when we put this, let's say sigma dot is equal to minus
mm,
k sine of sigma.
uh,
So how the finite time convergence of this differential equation
uh,
is known?
uh,
So why this differential equation is finite time stable?
uh,
है ना? So either I was thinking either we take that proof,
mm,
or we talk about this unmatched and unmatched disturbance and all that with example, and we talk about the finite time convergence in the next lecture. So then I thought let us first clear out what we started with this equation, है ना? And then we will talk about what is the how we can show that this is finite time stable, and what are the other methods to show finite time stability, to prove finite time stability, है ना? So that also I have to I know I have to take that, right? So is that okay, no?
yeah, so I think if you are doing matched and unmatched uncertainty, that's all right, because we have to uh, we have to cover both part. So either way, it's okay.
Yeah, yeah, okay.
So if you are thinking to cover matched and unmatched uncertainty today, so we'll cover that. Okay, and then we'll talk about the finite time stability next time. So it will cover both the finite time stability as well as robustness.
Yes, yes.
Okay.
Okay.
Okay. You please proceed.
Yeah. So then, yeah. So then, as I was saying that if you see with this analysis, and this analysis we can do it again, but I am trying to avoid it because we did it last time. That why how we derived this condition last time, k greater than f divided by g small m. We had derived it last time. If required, I will derive it offline and I will keep that derivation in this particular file. But we had derived it that k greater than f by gm will give us finite time stability of this of this differential equation one. This one will become stable if u is this and this, and there is nothing unmatched about this disturbance, matched or unmatched. So now the thing is, where does this unmatched disturbance trouble us, and why does sliding mode community and people talk about that unmatched disturbances are bad and sliding mode cannot handle it. And here we see that even without any matching conditions on d, we have been able to achieve finite time convergence of sigma. So sigma has reached in sigma has become zero in finite time, trajectory has reached the surface in finite time. So then how does unmatched disturbance trouble these things? So now uh, we see that we observe that in sliding mode control there are two things. One is reaching to surface in finite time, surface in ft, that is first thing. And second thing is the stability of zero dynamics. Now unmatched disturbance does not affect this. So unmatched disturbance, if you have somewhere unmatched disturbances, disturbance does not affect this component. So even with unmatched disturbance, you can achieve finite time convergence of sigma. There is no problem there. That just like that we have demonstrated here, that even if whatever kind of disturbance we have, we can achieve finite time convergence of sigma. But the problem arises in the stability of zero dynamics. The unmatched disturbance will cause problems here. So we will have problems in stability of zero dynamics. So after we are on the surface, we stay on the surface, but if there are some unmatched disturbances, then the zero dynamics will not be asymptotically stable. That means all the states will not be able to go to zero asymptotically in the zero dynamics. Some of the states will remain just bounded because unmatched disturbance is assumed to be bounded. So if this disturbance is bounded, so then those states will have to follow that disturbance. And we will see this with a very simple second order example. So now we will say that x belongs to R2, and we have these two equations. X dot x1 dot is equal to x2, and then x2 dot is equal to ax plus bxu plus we'll take here same dtx. So now here this dx, here this dx was in Rn, because this vector equation to make sense, this dx, this dtx here was in Rn. It was a vector, if, adding in each state like this. Here this dtx. Now this dtx is in just R. It is just a scalar disturbance that is affecting this x2 x2 dot equation. Okay, so now we have taken this one specific example, specific system. It is although it is second order, it is quite fairly general system, I would say, because all the Lagrangian modeling give us second order. For each degree of freedom, we get a second order differential equation in q double dot. So we get some equations like q double dot, and then uh, this q will be taken as x1, and q dot will be taken as x2, and you will end up in this differential equations, right? So although they seem very restricted, these two equations are very fairly general. You can generalize this equations according to ax and bx. So those terms we will get there. uh, now now again, let us see what we did earlier. We defined a sigma. Now we uh, say, let's say we are measuring x1 and x2 both, and we define the sigma like this, a simple line. uh, Instead of k, let me use m. Yeah, so x2 plus mx1. This is the sigma of x I will define. Okay, and then what happens when sigma is equal to 0? When sigma of x is equal to 0, this implies this algebraic relation is active, and this implies x2 is equal to minus mx1. And the zero dynamics, now zero dynamics for this sigma, for this given sigma, zero dynamics are x1 dot is equal to minus mx. These are the zero dynamics, right? And and when we want to design the sliding mode control to make this sigma is equal to 0, what shall we do? We will find the time derivative of sigma. That will be x2 dot plus mx1 dot, that will be equal to ax. I'm just using these two different axes to denote vector and a scalar, right? So it is just a habit. This x denotes vector and this x denotes scalar, right? So x2 dot is this pxu plus mx2. Now we can see that this sigma dot is equal to ax plus mx2 plus dtx plus bxu. Okay. So now this entire thing we can call as fx, and this is an bx. So this. So now we have our sigma dot in this form again, fx plus gxu, and with appropriate assumptions again on fx and gx, this control u equal to minus k signum sigma will make this sigma 0 in finite time. When this sigma 0 becomes, then sigma becomes 0 in finite time, we have this zero dynamics, x1 dot is equal to mx1 and x2 is equal to minus mx1, right? So these two, so then when the sliding starts, the entire system order is reduced. That x1 dot is equal to minus mx1 is one differential equation, and x2 dot is equal to minus mx1 is the algebraic equation. So one differential equation and one algebraic equation will define the motion of the system. Both the states can be found using this one differential equation and second algebraic equation. So that is what sliding mode community does. Uh, is sigma Lyapunov function or energy function? Yeah, as Mangal has said, we have not talked about Lyapunov function yet. Sigma is not Lyapunov or energy functions. Yeah, sigma is our surface function, switching function, based on which we are defining the surface. Right? So sigma of x is just a function of x. Sigma of x is switching function. Switching function. And what is surface then? The surface, switching surface is the level set. In that geometric mathematics, they are called is level set. I think that is the notation, sigma inverse 0. That means it may, so this notation I am not sure about level set, but this means that the set of all x where such that sigma of x is equal to 0, right? So that is our surface we are taking. You will get many surfaces for different values of this 0. uh, Sigma x equal to 1, you will have another surface. Sigma x equal to 2, another surface, right? So we are, so surface and switching function are different. So you have this is a function, sigma of x is just a switching function, and the surface is the set of points in your state space where that function is 0. You can have some other value of that function also. You can say that uh, you want to make a surface where sigma of x is equal to 5. Fine, that will give you some surface, that will give you some another surface, like that. So surface is level set of set points x where sigma of x becomes 0, and sigma of x is just a switching function which we have designed, or we have it as an output. An output can also make you give you a switching function, and you can have a surface with the level set of output also. Okay. uh, yeah. So then, yeah, so then this does it. So this is your example, second order example, which fits into this category. And now here we have this dx, which is coming in the equation, state equation where input is acting. Now we let us take another example where we have some disturbance like this. X1 dot is equal to x2 plus, we'll call it du tx, and x2 dot is equal to ax plus bxu plus dmtx. Now here again du and dm both are in R. They are not vector. The complete vector will be d. The dtx, if we want to take it, then we will take it as uh, du and dmtx. So this is the disturbance vector, and yeah. So now this disturbance with the subscript m, d sub m is matched, and d sub u is unmatched disturbance. Now what this disturbance causes trouble where? Now let us again do the same analysis, and we'll immediately see the trouble this disturbance can cause in stability of zero dynamics. Correct? I think uh, you may already see it immediately. So you have this surface, same surface, x2 plus mx1, and when you make sigma is equal to 0, that implies the algebraic identity x2 is equal to minus mx1. uh, Now when you make sigma dot 0, so for making sigma dot 0, we will get x2 dot plus mx1 dot. I think I made a mistake here. X2 dot plus mx2. Oh, right. Yeah, I have written mx2. Yeah. Okay. Okay. So now we have here ax plus bxu plus dmtx plus mx2 plus m dutx. So then we have this ax plus dmtx plus mx2 plus m dutx plus dx. Right? Now this entire part becomes fx, and this is your gx. So similarly, sigma dot is again fx plus gxu with both the bounded. We are never going to assume unbounded disturbance. So du and dm both are bounded. So du is also bounded, this dm term is also bounded, states are bounded. We know this maximum values, these states can take some physical variable, they are this ax maximum values are bounded. So we know this fx is going to be bounded, and we assume the bound to be known. Gx has to be lower bounded, otherwise we have problems in controllability. Now now so this stability of this sigma, and again u with minus k signum sigma uh, stabilizes with k greater than f by gm, stabilizes this sigma dot equation in finite time, and sigma becomes zero in finite time. But then uh, what happens to the zero dynamics? Now if we want to find the zero dynamics, when sigma becomes zero, we have the equality here. When sigma becomes zero, this equality becomes active. We have this equality. Now if we put this equality here in this differential equation, so x1 dot is now equal to minus mx1 plus dutx. Now we have problem in stability of this differential equation. Earlier we did not have that problem. Earlier, the when the zero dynamics became active, these were the zero dynamics, and the stability of this zero dynamics was guaranteed. Now we know this as a stable differential equation. We can show it easily, and anyone who has done any course in control system knows that this is a stable differential equation, and there is nothing to discuss about it. But now we have a problem with this zero dynamics. So when we have this unmatched disturbance, then zero dynamics are this, and this is not stable, or you cannot make never claim that this differential equation is asymptotically stable at least. So this is not going to be asymptotically stable with the assumption on du that it is just bounded. So this is with this assumption, you can never claim that this differential equation is asymptotically stable. It will only be bounded, and that bound will depend on this. So x1 cannot reach zero in this case. X1 will not be able to reach zero. What can happen though is uh, x2 can reach zero, because this is basically x2. This you have as x2, and if you need the stability on x1 only, uh, so then what you can say is that, because if you want the x1 to be zero, so then you need x1 dot to be zero, the derivative of x1 has to be zero. So if the requirement is this, then what can happen is that this x2 may become, you can make say x2 will become du tx. This is what you can do, and how people deal with unmatched uncertainty in sliding mode control. And there are some methods of surface design also. Here we have not put any thought in surface design. Our surface design is this is our surface design. So there are methods proposed to design a robust surface. So when that the zero dynamics come into picture, so then this is whatever appears here is some kind of robust control, and that robust control is such that they can handle this or minimize the effect of this unmatched disturbance on the stability of this equation, right? So then there are various notions, and this is one of the notion I am telling, that if we uh, do this, that x2 of t tracks this disturbance, right? So x2 of t becomes this disturbance, then only we can guarantee the stability of x1, right? So x1 dot to be zero, this x2 has to be equal to this unmatched disturbance. So in that case, what happens is that x2 becomes this disturbance, x2 is equal to this disturbance, so x2 will oscillate, or whatever this disturbance is doing, that will be the job of x2, and x1 becomes zero. So you get stability on x1 but not x2. So for the state, for the entire state, which is your vector x1 and x2, you cannot claim stability. This state will always remain bounded. A state will never become zero asymptotically. So asymptotically, just asymptotic stability of this state cannot be guaranteed, right? So asymptotic stability guaranteed. Okay. Alright. So I think this clears it. So this is about matched and unmatched disturbance and what problem, where do they cause the problem. Uh, DUTX known to us? No, DUTX is not known. Its bound may be assumed to be known. DUTX is the disturbance. We don't assume any kind of disturbance to be known. We may assume that the bound of the DUTX is known. है ना? So then, uh,
Actually, Prasidh, why the Jitendra got confused when you say that if you track x2 equal to du, okay, so he's maybe he get confused
okay,
how
okay.
you are tracking the du because you
No,
don't
no,
know.
yeah, yeah, yeah. So the control is designed. Control is designed in a way that x2 will track du. है ना? So control will be designed. So control is such that it will make this x2 state track disturbance so that x1 state can go to zero.
So what happens? Maybe Prasidh, I think his confusion because we don't know the du, and
Mm.
our controller now maybe we have to have some estimator, right? Observer. Huh?
No, yeah, correct, correct. I know what is. So this is the idea. This is
Uh,
the idea that is used in disturbance observers.
yes. Uh,
So now you have the disturbance observer here. So you have made a control.
mm.
You have made some functions, control functions, which will make some state uh, track the disturbance. So this x2 hat, you have some auxiliary system just we make in observers, and then you apply that control there, and then this state will track the disturbance, and then this state which we have in observer you can use as disturbance observer. This is the idea behind disturbance observers. है ना? I think was that the issue? That is, yeah. So Mangal sir has rightly understood Jitendra's doubt. That Jitendra wanted to ask. Correct. Okay. So is that clear? Okay. So then, yeah, Jitendra has said yes. Okay. So then, uh, right. So what I was telling is that whenever we have unmatched disturbance, we see unmatched disturbance, we can be assured that it does not cause the finite time stability problem. It does not cause problem in the finite time convergence on the surface, but it causes problem in the stability of zero dynamics. So zero dynamics cannot be ensured to be stable, even asymptotically stable in those cases when we have this kind of disturbance which does not come with the input equation, right? So this kind of disturbance which does not come with the input equation, this disturbance these are unmatched one, है ना? And these disturbances are the matched one which come with the input, which are affine with the input equation. And then when we uh, simplify all these analysis for the linear systems, LTI systems, then there are specific conditions. People say that the disturbance is in the range space of input matrix. That is, we have this B, capital B, when you have this x dot is equal to ax plus bu plus d. No? So let's say dtx here also. So then you can say that this dtx is a vector, and this vector belongs to the range space of B, which is nothing but saying like this, it comes with the input. The disturbance is affecting the system with the input. The disturbance is something like this, right? So So those kind of conditions can be derived for linear systems, and you may see it in the literature. uh, okay, so yeah, so I think this matched and unmatched disturbance part is covered, and I believe it is clear. uh, yeah. So then I believe next thing we can talk about is this finite time convergence. है ना? So let's see how to take this finite time convergence. Let us take this first equation itself. This sigma dot is equal to minus k sine of sigma. Hmm? And then we claim that this differential equation is finite time stable. Why, how can we justify our claim that this differential equation is finite time stable? So there are several ways to do this. The first way is, I think probably we can separate this differential equation in with according to sigma. Let's say when sigma greater than 0, assume sigma is greater than 0, uh, then sigma dot is equal to minus k, right? And then we can just integrate this equation. The solution of this integral, the solution of this equation we can find, and then we will find that sigma of t becomes 0 in finite time. Sigma, there exists a time, there exists a time. Let me write it in this manner only. There exists a time tr such that sigma of t is equivalent to 0 for all t greater than tr, right? Similarly, for sigma less than 0 also, you can uh, sigma dot is equal to k, and sigma is less than 0. We can integrate this equation, simple equation again, and again we will find a time tr for which sigma becomes 0 in finite time. And this does not happen when you have the equations like this. Sigma dot is equal to, if you take minus k sigma, then you cannot, this condition does not occur there. You cannot find a tr, finite tr. You cannot find a finite value of tr such that sigma becomes 0 for all times greater than tr. This does not happen for
So Prasid,
equation.
so I think a couple of lecture back you have derived that also. You have written sigma or t of equal to minus kt plus some c or some things, right?
Yes, correct, correct.
So you have written maybe above, and then you have taken the both positive and minus negative side.
Mm.
Uh,
Yes.
and then I don't know whether you have seen you have that also or not in your slide. Maybe uh, let's see.
No,
So now
I
the
think in
question.
the previous lecture only I did that. In
So
the
previous
previous
lecture.
lecture it was done.
So maybe it's there in the video. That's all right. See, when
Mhm.
it start with the say uh, some value where sigma is greater than 0. Now when maybe it intersect say this 0 sigma equal to 0. How do this equation or may not say that it will last time you have talked, but explicitly does not say how it will stay. And I think that is a question also.
Mm. How in what sense? I mean, the solution. So now this differential equation is a discontinuous one,
Hmm.
right? So there is a discontinuity in the right hand side. So the solution of this differential equation
Hmm.
will be understood in the Philippos sense. Okay? So we will
So
say,
I'll repeat. So what Viswendra is telling, sigma dot equal to minus is a not sliding mode control. It's a sliding mode control, right? Sigma dot.
okay, yes, there is something. Let me read. Is it not sliding mode control? Then since it does not have finite.
Why you are telling that it's a not a sliding mode control? Hmm.
I think you can unmute and
Viswendra,
ask.
you can say why you are telling it's a not a sliding mode control.
Hello, sir.
Uh,
I want to know that if there is no finite time stability, if it is going to stability in infinite time or asymptotically it is going to stability, then is it still sliding mode control or
No,
something
no,
else?
no, no finite time stability. If there is no finite time stability, then there is no sliding mode control.
Yes, so that's what I wanted to confirm. So
Yes,
it's not sliding mode control if it is minus k sigma.
correct, correct. It is not.
Okay,
And
thank you.
even the sliding mode control purists. Just a minute, let me. Yeah. So even sliding mode control purist will say that only finite time stability is not important for sliding mode control. You can have the equation like this also. You can say sigma dot is equal to minus k 1/3, and this will give you finite time convergence of sigma. But sliding mode community purist will not consider this also as sliding mode control. है ना? So sliding mode control must have a certain kind of robustness. What they say is that sliding mode control must have certain kind of robustness, and that kind of robustness is not possessed by this control. The kind of robustness that we talked about here, that uh, if you have this disturbance bounded,
So,
so
and
this is
the reason could be because see sigma went zero, so then zero dynamics there is no disturbance. Huh? So the like see although there could be unmatched disturbance, but assume that there is a no unmatched disturbance, then zero dynamics will always slide on the or will maintain that algebraic and differential equations. So that will guarantee the robustness because all disturbance is acting through the x2, right?
yes,
Huh?
yes,
But when you take this fractional order, right? Please come
mm,
down.
yeah,
So when you take the fractional order, ideally also it will drive the sigma to zero, right?
yes.
But then
But
why? So once we have a sigma equal to zero, the disturbance cannot enter in zero dynamics, right?
no, but the thing is that you see here, let me show that.
Hmm.
Yeah. So here,
Hmm.
when we took
Hmm.
this D is taken.
Hmm.
The condition on this D, I
Hmm.
have not written it here. Let me write it there. That dTx
Is a bounded.
is bounded by a constant D.
Yes.
Correct.
Uh,
And let me say dm.
uh,
With this boundedness
uh,
assumption,
uh.
we were able to show this part, this and this.
Yes.
We have not shown it yet, so we can like in previous lecture we I have shown it, but so
F by G, yes. That K you will choose such by that F by G that it will guarantee, right? That's what
correct,
you.
correct, correct. So this with this k greater than f by gm,
Uh,
we can we can ensure the finite time convergence of this differential equation.
uh.
But if you have a control like this,
So that
then
is
you
a
can.
reduced order. After that, I don't know. This is a this is not a control. You are putting like so instead of sigma, the confusion why
Yeah,
it's created.
correct, correct. Yeah, yeah. So instead of here,
Uh,
here, let's say you have this u,
uh,
and instead of k sigma max, you
uh,
put u is equal to minus k, let's say sigma raised to 1/3.
uh,
है ना?
uh,
So here when you put this minus k,
uh,
this u is equal to minus k
uh,
sigma raised to 1/3,
uh,
then you cannot ensure
uh,
the stability, the finite time stability.
hmm,
है ना? Under this disturbance, under these uncertainty conditions. What is the uncertainty condition?
uh,
Uncertainty condition is this: fx less than or equal to f, and 0 less than gm less than or equal to gx.
uh,
So under this uncertainty condition,
hmm,
this control cannot ensure the finite time stability of sigma dot.
hmm,
It does not have the same robustness property.
hmm,
It has some robustness property which may be more than the normal just k minus sigma, है ना? Minus k sigma, just linear control. It has some better robustness property than this, but it does not have the same robustness property which comes with this k signum sigma.
hmm.
You cannot do that. it is not possible to prove this stability. In fact, you can prove that it will not be finite time stable, and it will only remain bounded. It will remain around this sigma equal to 0. It can never reach the sigma equal to 0 in finite time. So this does not have the same robustness property. That is why this is not called uh, sliding mode. So they don't call this sliding mode control. If you have something like this, then it is not sliding. Although finite time convergence is there, that is a good controller. One can say it can make a good controller. You can have finite time convergence controllers in absence of disturbances, but when the disturbance, and it can give you finite time convergence in some other kind of disturbance. So what the point I forgot to make is that, so with these assumption, on disturbance and uncertainties, this controller cannot guarantee finite time convergence. But you can put some other assumptions on F and G. Some assumptions which depend, where the bounds depend on uh, X. Right now, these bounds F and GM, these are just constants. They are not dependent on the states. So if you put these bounds, these disturbances, these uncertainties are also dependent on state, meaning that when the states are going near origin, those uncertainties are also reducing. They are also, their values is also becoming less. Here, this is more stronger, that is a more restrictive assumption on disturbance, that you want the disturbance, these uncertainties, to reduce when you go near origin, and this allows the disturbance uncertainty to be as large as possible even near origin. Even when you are near origin, this fx is allowed to take this value capital F, uh, and still you have finite time convergence on sigma. But if you use this kind of control, then you will have to put an assumption on this fx such that this fx becomes less as you go near origin. Then you can prove the finite time convergence of this sigma. If interested, I can perform that analysis. I don't have that analysis ready right now, but I remember doing it, and we can do that. We can do that, how, what kind of condition is required on F and G, so that this can also uh, give you finite time convergence on sigma. But with this condition, it cannot give. It is not possible. So if we required, if interested, we can do that also. I will do that analysis. And in fact, it is better that students do that, because it will be a good, because if they are doing research, then this kind of analysis, I am making one statement, so they just keep in mind this statement and try to do this analysis on their own. Yeah, so Jitendra has some question. With U is equal to minus K sigma become linear control, however, it will not be non-linear. I did not understand this.
Prasid, so if we are done, I can stop recording and then we can take questions, right?
Yeah, okay, no problem. Yeah,
So we are not covering, right? The next lecture you will cover this finite time convergence, right?
correct.
Okay, in detail.
Yeah.
Okay.